Welcome to the lectures on modern digital communication techniques. Yesterday or in the previous lectures, what we have seen is that how to represent a band pass signal in its equivalent low pass form. So, just to summarize, we had taken a signal whose frequency coverage was represented by a figure something like this, right, and we said we want to represent the low pass equivalent form. So, what we did is because of symmetricity, we said that you could take only the positive set of frequencies, and that was given by 2 u of f times s of f, right, and then we converted this to its equivalent low pass by simply doing a frequency translation, and then we got the relationship. And in summary, what we had established is that S of t, that is the real signal in passband, you could represent it by real part of SL t e to the power of j 2 pi f c t. This was one of the forms, and naturally this could extend to if SLT is represented as, if you write SLT equals to x of t plus j y of t, if you would represent it in this way, then one would get x cos minus y sine. In short, I am writing this, and one could also represent SLT as a t e to the power of j theta t, and in this case you would represent this by a t cos 2 pi f c t plus theta t, right. This is what we have discussed in the previous lecture. So, now after having discussed these things, we would like to look at a few properties of this, or a few more relationships relating the passband spectrum to the low pass equivalent spectrum. So, for that what we do is we write S of f is equal to minus infinity to infinity S t e to the power of minus j 2 pi f t dt. So, this is the Fourier transform of S of t, and this one we easily replace S t by real part, that is what we have here, S L of t e to the power of j 2 pi f c t. That means S of t is replaced by this part, e to the power of minus j 2 pi f t dt. So, if I have, let us say, a real part of something. So, if I have real part of, let us say, zeta, I could represent it as zeta plus zeta conjugate and half of that. So, if you take this, you get the real part. Accordingly, we will do the same for this. So, what we do is we put a half straight ahead, then an integral remains as it is, and this translates to S L of t e to the power of j 2 pi f c t plus S L conjugate e to the power of minus j 2 pi f c t and e to the power of minus j 2 pi f c t dt. So, this is the representation, and now we will use a few of the Fourier transform properties that we have described in the previous lecture. So, now you will see how these properties come handy. So, we know that if S L of t has a Fourier transform pair of S L of f, in that case you could write S L of t conjugate has a Fourier pair S L conjugate of minus f, and then we could also state that S L conjugate S L of t e to the power of j 2 pi f c t would have the pair S L of f minus f c, and similarly S L conjugate t e to the power of minus j 2 pi f c t would have S L minus f minus f c conjugate. So, this is the relationship that we are going to use. So, then we could write that from whatever we have here in the last expression is equal to half So, if you see the first, it is the Fourier transform of SLT e to the power of j 2 pi f c t, and if we say SL is the Fourier transform of SLT, SLF is the Fourier transform of, is the inverse of SLT, then we could use this relationship SL f minus f c, and if you look at this, this is the conjugate of this, and hence the conjugate would turn out to be SL conjugate minus f c. So, what we see through this particular relationship is that the spectrum that we have on the left, the spectrum of the real band pass signal can be represented in terms of its equivalent low pass signal. So, that means the spectrum in the pass band can be related to the spectrum of the equivalent low pass, where we had already stated that SLT is the representation of the equivalent low pass of ST, and we have gone to S of f and we have related S of f. If we place it this way, it will be clear. ST, SLT, SF. Now, what we want is a Fourier relationship of this, and ST we have represented in terms of SLT. So, from ST we have gone to its low pass equivalent, and then we could connect the spectrum to its low pass equivalent. So, thereby again we are saying that at this point, that if we have the low pass equivalent, then it could relate to the pass band. So, we can get the pass band from the low pass equivalent. So, this is what we set off our discussion with initially, that we do not need the carrier representation, we can do with the equivalent low pass, and we have seen a second step whereby we could connect the pass band spectrum as well to the low pass spectrum of that particular signal. So, after having covered this, we would like to calculate the energy of the signal S of t. There again we are interested in seeing what is the relationship between the energy of ST and that of SLT. So, we set forth in calculating the energy as E is equal to integrate minus infinity to infinity S squared of t dt, and that you could do in many ways. You could again go by writing real part of SLT e to the power of j 2 pi f c t squared dt. Real part would be SL cos component of this with the x and y, of course. So, you could also write this as if you would recall the other representation that we had here, we had this kind of a relationship. So, where AT is equal to mod of SLT. So, if you do this, then what you are going to get? You are going to get the relationship as you are going to get this representation. So, you can get it as AT e to the power of j 2 pi f c t plus theta t in the inside, and you are going to take the real part of it. So, you are going to take the real part of it, you are going to get cos AT cos of 2 pi f c t plus theta t. This is what you get inside this box bracket, and there is a squaring of it. So, you are going to get a squared of t and cos squared of 2 pi f c t plus theta t. Now, this cos squared term you could replace in terms of cos, that means you are going to have cos squared theta minus sin squared theta equals to cos theta. So, from that you could get cos squared theta minus 1 plus cos squared theta equals to cos theta. So, which basically gives you that cos squared theta is equal to 1 plus 1 would go this side, cos of 2 theta upon 2 because you have a 2 over there. So, you are going to get a squared of t half cos of 2 multiplied by whole thing, that is 4 pi f c t plus of 2 theta t. So, this is what you are going to get inside. So, sorry, you are going to get 1 plus of this. So, I could put a chain bracket there, plus 1 and 1. So, now the representation that is there in front of us, we have 1 with a squared of t. So, basically, and there is a half over here. So, you are going to get half integral minus infinity to infinity, and a of t is basically SL of t. So, you could simply write mod of SL t squared dt plus, of course, you have the second part of it, which again minus infinity to infinity mod of SL t squared times cos 4 pi f c t plus 2 theta t dt. So, now definitely this SLT is the low pass representation, this is the carrier frequency, and we have said that the bandwidth of this is much smaller than FC that goes by here. So, its coverage is much less, so that when you get back to the baseband you have like this. So, this is much less than FC. Going by that, this fluctuates very slowly compared to this, and cos to 4 pi f c t is basically oscillations like this, and if you integrate it, it turns out to be a 0. So, from minus infinity to plus infinity, because of in one cycle you are going to integrate to 0, and there are so many of them. So, this could be approximated to half, and if you look at this, this is the energy of the low pass equivalent signal. So, all that we have at this point is that the energy in S of t is represented in terms of the low pass equivalent. So, that means again what we are saying is that we can calculate the energy of the passband signal given the low pass equivalent representation. We have already seen that you could connect the spectrum, and now we have seen that you could also calculate the energy as well. So, moving ahead further, we are now in a position where we say that we can relate the low pass equivalent of the signal to its passband, and any signal that we have passes through a band pass channel. So, we also need to represent the channel in its low pass equivalent form. We have already described that the channel is or the signal is conditioned in such a way that this picture we had drawn before, this is the f and this is, let us say, the channel gain. So, a channel could have a gain like this, and you would like to restrict your signal to this particular band within the channel, and the center of it is FC. Generally, we send signals in this form. So, since the signal is going to the pass band, or in other words, we have the pass band signal and we are bringing it down to its low pass equivalent representation. So, if we have to analyze a system, we should also find the equivalent representation of the channel in its low pass equivalent form. So, if we do this, we can say that let us consider a channel which is band pass channel. So, in other words, we have to first say that the band pass signal passes through a band pass filter, we can say channel, right, and we would consider, let us say, h of t as the channel impulse response. You can also think of this as the impulse response of a band pass filter. You can also think it the channel as a filter, which we have partially described before, because when we launch some signals into the channel, some of the signals will get attenuated, some of the signals will pass through. So, that means the channel is acting as a filter. So, in case of linear models, we can think of a linear time invariant system we have described in one of the very initial lectures. So, now we are considering the channel equivalent to a filter, and that has an impulse response h t, which is real Remember, we have said the signal ST is real. The real signal ST is in the pass band, because in the pass band you don't have an imaginary signal, you are having real signal which passes through real channel. So HT is real, and if HT is real, by Fourier relationships we would have H conjugate of minus f is equal to H of f. This relationship we had proved earlier when we were looking at properties of Fourier transforms or Fourier transform pairs. So again, you see that Fourier transform plays a very important role in the analysis of these signals, and in some sense you would argue that we are still in the analog domain. The statement is very correct, but what we will be doing is we will be impinging digital signal at some point onto these. So we need an accurate representation of this. Without doing an accurate representation, we will not be able to harmonize or connect each part of the input to consecutive parts and finally reach the output. So to do that, we started off with the signals. So some of these things might be very similar to your analog communications, but finally this would help us in setting up the basic expressions for digital communications. So all we are doing at this point is harmonizing the expressions so that we use a uniform notation throughout. So we have this relationship, and what we would do is we would define a channel where we would say that H L of f minus f c is equal to H of f for f greater than 0 and is equal to 0 for f less than 0. So this is again in the form that we have defined earlier. We had said that S L is equal to S L of f is equal to S plus of f plus f c, if you would remember this, and definitely S L of f minus f c is equal to S plus of f, right, which is equal to 0 for f less than 0. So this is exactly what we have over here, and this had happened because it is real, which had a symmetric frequency domain representation, and for a symmetric frequency domain representation we can take only the positive frequencies, and by a frequency translation you can have the low pass equivalent representation, and a similar thing is happening over here. Only thing is that we are beginning with this definition. There we started with the real time signal. Here we are saying that let us define it in this way, and in a few steps you could also have, for example, if you would say we want to actually go through the steps, f minus f c we have already written equals to H of f for f greater than 0, and you could say H L conjugate f minus f c is equal to H conjugate of f still for f greater than 0, and then you could say H L conjugate minus f c is equal to H conjugate of minus f greater than 0 would mean f less than 0. So then we have this thing for f less than 0, which is equal to 0 similarly for f greater than 0. So these are the two steps by which we define the particular channel, and going by this you could say that H of f, you could write it as H L f minus f c, which is for f greater than 0, plus H L conjugate minus f c for f less than 0, as is clearly evident from this. So once we have written it in this form, we would be interested in relating this to H of t. So to get H of t, you are going to take the inverse Fourier of H of f, and hence inverse Fourier of the right hand side as well. So this inverse Fourier of this would be represented by Ht. Of course, we have said Ht is the impulse response, and if you take the Fourier transform Fourier relationship, reverse direction is the inverse Fourier relationship, right. So that is what we have. H of t is equal to, so H L of f minus f c would result in H L of t e to the power of j 2 pi f c t, going by our earlier derivations, if you would recall the derivations that we did a few steps back. over here, right. We had used these relationships here. So, using the same relationships that we have represented here, we can actually carry forward here, and we can say that this is here, and similarly this one will be HL conjugate e to the power of minus j 2 pi f c t, and hence it is clear that you could write this as 2 times the real part of HL of t e to the power of j 2 pi f c t. So, where you again see that the relationship looks very similar, except that there is a 2, and of course, this is to normalize the power that we have got in. So, we are again back to same form of representation that we have done for signal, and now we have seen the relationship that would exist between the passband channel coefficients and that of its equivalent low pass representation. So, since we have got these relationship, of course, just at this point we would like to recall that similar to what we did earlier, in general we should say HL of t is complex. We have not said about HL of t, we have said HT is real, we have not said HL of t would be real. So, in general it is a complex, and when you handle complex signals you will get to see that how do we get HL as complex. So, that we are going to proceed very soon. So, now since we have seen signal, we have seen system, what do we need now? We have a signal with us, we have representation of the system. So, the next very important thing that we require is the response of a band pass system to a band pass signal. So, that means we need to connect these two, and we have to show that how these could relate in terms of the low pass equivalent representation. So, let us proceed with this. So, we would say that the output now, since at this point I would like to say that since we know that the relationship between the pass band and the equivalent low pass is of this form, it has this kind of a structure, right. In both the cases we have seen. What we have with us is a signal in the pass band and a channel in the pass band. So, the output will also be in the pass band, right. So, we can say that if signal is in pass band, channel is in pass band, definitely the output is also in the pass band, right. This is for sure. And so, now what we have with us is the signal which is coming out of the channel is pass band. So, once again reminding you, pass band signal getting into the channel which is pass band, of course reminding you here. So, definitely the signal that comes out will also be in this band, right, except if the channel is not translating the frequency. If the channel translates the frequency, what does it mean? The channel translating the frequency means it is doing some kind of a modulation. So, we are not looking at those kind of channels, okay. We are just looking at linear channels which will not play around with the frequency components. So, now we have a pass band output. So, we can say that the output R of t which is in the pass band, we would like to relate it to the low pass equivalent, and this will be handy for us. So, we will say we could write this as real part of, let R L t represent the complex envelope of the low pass signal e to the power of j 2 pi f c t. Going by the earlier things, we can say this kind of a relationship should definitely hold between the pass band and the low pass signal, okay. And then we should say that how do we get R of t, since R of t is the output of a filter whose impulse response is given by h t and the signal going into is s t. So, definitely the output is the convolution of st and ht, and that we would write as integral minus infinity to infinity s of tau h of t minus tau d tau. So, at any instant t, we have a convolution output of the signal along with the channel impulse response. And if we take the Fourier transform of this, that means we are going into the frequency domain to do this analysis, right. We will be always going into the frequency domain back to time domain, because we want to find all kinds of relationship, and often some operations in the frequency domain turn out to be easier. So, what we have is, if we do a frequency domain, we will have R of f, where R of f is the Fourier transform of R t. So, that is the relationship. Okay. R of f is equal to S of f. Because there is a convolution in the frequency domain, it will be a multiplication, right. So, we have this relationship in the frequency domain, right. So, in this particular lecture, we stop over here. In the next lecture, we would like to continue with the derivation of the time domain corresponding to these expressions that we have here, so that we can relate R t to R L of t, and we have this functional relationship. So, we stop this particular lecture at this point. We continue with this in the next lecture. Thank you.